Let's talk about the art of industrial balance, specifically leveling rotating equipment. When you picture a massive industrial plant, you probably think of endless pipes and colossal towers, right? But the real beating heart of these facilities, it's the rotating equipment. We're talking massive pumps and compressors. Today, we're diving into exactly how field engineers install these multi-ton machines and balance them to within a fraction of a millimeter. It's actually pretty mind-blowing.
So here is the multi-million-dollar question we're answering today. How do you perfectly level equipment that weighs as much as 2 elephants? Imagine a crane has just lowered a gigantic pump onto a concrete foundation pad. Now, to the naked eye, that concrete looks flat. The bottom of the pump looks flat, too. But in the high-stakes world of high-speed rotating machinery, looks flat is basically a recipe for catastrophic mechanical failure. If a machine spinning at thousands of revolutions per minute is even slightly tilted, it's going to vibrate, tear its own bearings apart, and literally destroy the piping attached to it. So how do we get it perfectly, undeniably flat?
To wrap our heads around how industrial engineers tackle this, think about a super common, everyday annoyance. You're at a cafe, you set your coffee down, and the table wobbles. It drives you crazy, right? What's your very first instinct? You grab a paper napkin, fold it up a few times, and wedge it under that short leg until the table stops rocking. Well, believe it or not, the core principle used to level a multi-million-dollar industrial compressor is exactly the same. It's just the wobbly table solution scaled way, way up to an extreme level of engineering precision.
But, out in the field, we obviously aren't using folded paper napkins. We use something called a shim plate. A shim plate is a highly precise, incredibly durable metal sheet, usually made of stainless steel. These sheets are systematically slipped underneath the equipment's base plate to make microscopic adjustments to its levelness. So if one corner of that massive pump is sitting just a tiny bit too low on the concrete, engineers will slide one of these precise sheets right underneath the motor foot to raise it up.
It is genuinely fascinating to see these shims in action. As you can see, they come in stacks and are manufactured to extremely precise, pre-measured thicknesses. Honestly, some of them are literally as thin as a strand of human hair. And you can see exactly how they're deployed on site. The shim plate is slotted right underneath the heavy cast iron foot of the electric motor, directly on top of the foundation. They usually have this U-shape, which is super clever because it lets them slide right around the anchor bolts that will eventually lock the whole machine down.
Okay, so let's break down how this actually looks as a field procedure. It all happens in 4 distinct steps. Step 1 is foundation placement. The crane lowers the equipment over the anchor bolts and onto the pad. Step 2 is shim plate insertion. This is where workers start sliding those U-shaped metal sheets under the equipment feet. Step 3 is the master level reading. They check their progress with a highly sensitive instrument to see if the machine is perfectly horizontal. If it's not, they loop right back to step 2, adding or removing shims. Finally, step 4 is bolting. Once that level is absolutely perfect, they tighten down the anchor bolt nuts to lock it in place. I mentioned a highly sensitive instrument in that 3rd step. Let's take a look at the tool making this all possible, the master level, sometimes called a machinist level. Now, this is absolutely not the cheap plastic bubble level you'd pick up at a hardware store to hang a picture frame. This is a heavy, precision-machined piece of metal. If you look at the glass vial right in the center, the tolerances on those markings are just wild. One tiny division on that bubble can represent an angle change of just 0.0005 inches per foot. To put that into perspective, this tool is so sensitive that the actual body heat from a worker's bare hands can sometimes warp the metal enough to completely throw off the reading. That is the insane level of precision we are chasing here. And this brings us to a really brilliant example of textbook engineering versus real-world field engineering. The textbook method is to place the master level perfectly flat on a specially machined surface right on top of the pump casing. That's exactly how it's drawn in all the manuals. But in the real world, out in the dirt and steel of a construction site, pump shapes are messy and complicated. Sometimes you just can't access that top surface. The casing might be in the way. So what do field engineers do? They improvise. A super common workaround is to place the level directly across the top face of the discharge flange. That's the perfectly flat steel ring where the piping will connect later. It's a highly effective, totally practical way to guarantee it's horizontal when your main access is blocked.
So you might be wondering, why go through all this painstaking trouble? Why obsess over literal fractions of a millimeter? Well, in plant construction, you aren't just tweaking things until they kind of look good. You're playing by strict rules, and the ultimate goal here is passing the official engineering inspection. Every single piece of equipment has a hard tolerance limit set by international codes and project specs. If you fall outside those limits, the inspector rejects the installation, and you are starting all over again.
Let's actually look at the numbers here. The inspector is checking 2 main things, elevation and levelness. For elevation, which is the absolute height of the equipment relative to the rest of the plant, the tolerance is usually plus or minus 3 millimeters. That means you have a tiny 3 millimeter window above or below the blueprint height. But then we get to levelness, or how flat the machine is. For a pump, it can only tilt a maximum of 0.5 millimeters over a 1 meter span. And for a compressor, it's even stricter. A compressor can only tilt 0.2 millimeters over that same 1 meter span. Why the difference? Well, compressors handle gas and operate at much higher speeds with way more intense vibrational forces than water pumps. The faster and more volatile the machine, the tighter your tolerance has to be.
Let's ground those numbers with a visual. This is an actual inspection diagram straight from the field. That point labeled A at the top flange, that's exactly where they check the overall elevation. Then look over at points B and C. Those are checking the nozzle levelness, making sure the pump isn't leaning forward, backward, or side to side. You can see the tolerance is written right there on the document, plus or minus 3 millimeters for elevation, and that incredibly tight 0.5 millimeters per meter for the pump levelness. The inspector is literally going to walk around with that master level, check these specific planes, and they'll only sign off if the bubble stays perfectly inside those microscopic lines.
Now, I want to share a bit of an industry secret with you, an unwritten rule that really separates the rookies from the veteran construction engineers. Even though the official blueprint says the elevation tolerance is plus or minus 3 millimeters, the golden rule on site is this quote right here. Construction engineers should not consider plus tolerance, only minus tolerance. So what does that actually mean, and why do experienced engineers pretend the plus tolerance simply doesn't exist? Think about the mechanics of what we've just been talking about. If your equipment installation comes in at a minus tolerance, meaning the machine is sitting just a tiny bit too low, how do you fix it? It's actually super easy. You grab a hydraulic jack, lift the machine slightly, and slide another one of those paper-thin stainless steel shims underneath. You can build it up fraction by fraction until it's absolutely perfect. But if you mess up and come in at a plus tolerance, meaning the equipment is sitting too high, you have a literal disaster on your hands. You can't just magically sink a massive machine into a solid concrete pad. Lowering the elevation is virtually impossible without completely tearing out the foundation or grinding away solid steel. So, aiming exclusively for a minus tolerance is this brilliant defensive strategy that saves multi-million-dollar projects from catastrophic delays.
We've just seen the sheer amount of manual labor, precision tools, and strategic thinking that goes into perfectly leveling a multi-ton machine. But here is a wild thought to leave you with. Let's say you've perfectly leveled the pump using those thin metal shims. The inspector has signed off. The master level bubble is dead center. But what happens if someone accidentally bumps the machine? Or what happens when a 500-pound steel pipe is eventually bolted to the top of it, completely changing the weight distribution? How do you make sure all this meticulous balancing isn't ruined the second everyone walks away? Well, that requires an entirely different, incredibly permanent process called grouting, where liquid concrete is poured directly under the machine to freeze those shims in time forever. But that's a fascinating engineering story for another explainer. Keep learning, stay curious, and I'll catch you next time.